Good afternoon. I'd like to begin by thanking Giovanni Jens and his organizing committee, and as well as acknowledging the Royal Highness for her presence today. I'd also like to follow up on what Mike just talked about. He did exactly what I had hoped he would do and give us a really great lecture on plasticity, specialization, and training. He's a tough act to follow. And the work I'm going to talk about today builds upon that. In fact, most of my work is centered around the notion of plasticity and then the concept of training. Despite the fact that my work mostly takes place in typical healthy children, training is still very relevant when we think about sort of the idiosyncratic experience that they have. And sometimes training is a positive thing when we think about physical activity and fitness training and exercise, proper nutrition, things like that. But can oftentimes be negative as well, as I'm going to lead into in just a minute, when we think about sedentary behavior and physical inactivity, poor nutrition, and the overconsumption of calories. And so what we know today is that this generation of children are becoming increasingly sedentary. There's this growing tendency among industrialized societies for children to participate in sedentary activities, which now compete with what was once physical activity time. Because of this, there is concern for the increased prevalence of being overweight and unfit. More than 1/3 of children, approximately 25 million youth in the United States, are considered overweight or obese at the moment. And when you look at dietary trends, what you can see is that we're not consuming the proper foods, and that is to say that it's awfully small here. When you look at proper nutrients like whole grains and fresh fruits and vegetables and so forth, we're not meeting the dietary goals that we've set for our country. But when we look at the things that we shouldn't be eating, such as calories from solid fats and added sugars, or sodium or saturated fats, you see that we have an overconsumption of calories. And so our diets are out of whack. And over the course of time, this type of training wreaks havoc on the body. And hopefully today I'll point out the brain as well. As a function of this, the obesity rates have skyrocketed. It doesn't look like, oh, there we go, it's sort of going slowly. What you're looking at there on the left is a map from the Centers for Disease Control and Prevention. And this map it doesn't look to be moving smoothly, or I guess it is, it's just not moving smoothly on my monitor. This is the rate of obesity in the United States from 1985 to 2010. And you can see where it moves from the lean blues to the fat reds. And the whole country is increasing in its body mass. On the right, what you can see is a snapshot of the obesity epidemic, or the overweight and obesity epidemic in school-age children from 2003 to 2007 to 2012. And this is one of the fastest growing populations of overweight and obesity. And so, matched with physical inactivity, we have a growing problem, no pun intended. The problem is that sedentary childhood often leads to sedentary adulthood. Kids have time, and with that time, they learn their physical activity patterns. And when they don't learn them as children, it's very hard to learn them as an adult when your time is taken up by family and work and other stressors. And so we really need this physical activity exposure as children in order to be healthy, active adults. Now, as a side here, I'll just give you a quick slide that I came across this work recently, where the U.S. Department of Defense has a different focus than ours on health and wellness, but they merge in certain spots. And it's scary to think that the Department of Defense estimates that 1/3 of military-age youth are now ineligible for service due to their weight. Nearly 27%, about 1 in 4, 17 to 24-year-olds are too overweight to serve the military. And according to a publication that the Department of Defense put out recently called Too Fat to Fight, they've spent more than $1 billion on weight management. And so there's multiple implications for this type of lifestyle. Now, Alarmingly, recent estimates have indicated that this generation of children will be the first in United States history to not outlive their parents. They're predicted to live shorter lives and less healthy lives than their parents. The problem is that schools, which stand to influence the vast majority of children, I believe that public schools account for 97% of the child population in the United States, these schools are exacerbating this issue of physical inactivity because our governments, through testing, have decided that time should be spent teaching to these tests or adding academic time at the cost of physical activity time. And to sort of jump to the conclusion of all my work, there's no evidence to support this. In fact, if you look through the entire literature base, there's two outcomes. The first is that physical activity is positively related to academic attainment. And the second is that there's no relationship. And that second case, that's still a win, because what we have is we have a healthier individual at no cost to academic attainment. And so schools are moving in the wrong direction, actually exacerbating this issue. Now, work in my own laboratory has supported this. And so this first study took place with about 260 kids from Champaign, Illinois, which is where the University of Illinois is. And these are 3rd through 5th grade kids. And what we have here is we went into the schools and we had children perform the fitness gram, which follows the President's Physical Fitness Test. And this is a physical activity test where they look at different aspects of fitness. And so the first would be a pacer test, which measures aerobic capacity through a shuttle run. There's measures of muscle strength through push-ups and sit-ups, measures of flexibility through a hamstring sit and reach test, and then a measure of body mass index to screen for body weight or adiposity. And what you can see is the number of tests in which each child passed, all the children passed of these 5 tests. And so some passed none of them, others passed 5. And on the y-axis, what you're looking at is their scores on the Illinois Standardized Achievement Test of math and reading. And quite simply, you don't have to spend your years doing science to realize that there's a nice relationship here between the number of tests passed and performance on the Illinois Standardized Achievement Test. When we broke it down and we looked at what aspects of fitness were related to achievement, what we found is that the aerobic capacity test was related, such that with an increased number of laps run, we saw increased performance on this test, so a nice correlation there. Muscle strength, muscle flexibility appeared unrelated, and body mass index had a small but negative relationship, such that an increase in body mass index was related to a decrease in academic performance. And so these data were really some of the first from my laboratory that paved the way for the work that we do. And really the vast majority of the work that we do utilizes measures of neuroimaging as well as cognitive tasks in order to understand underlying aspects of everyday cognition and behavior. And we look to see how different health behaviors or markers of health behavior influence these aspects of brain and cognition. And so the first one I'm going to talk about is relational memory. Relational memory is oftentimes called associative memory, and regardless of what it's called, it's basically hippocampal-dependent memory. And so the hippocampus is a subcortical structure in the brain here, and it's involved in aspects of memory. This particular structure is very well studied in rodents and other animal models, particularly related to relational memory. And all the animal literature, a lot of the animal literature is focused on, in my area, is focused on fitness or proper nutrition or poor nutrition, and we look to see how plastic the hippocampus is and how these rodents behave as a function of as a function of the introduction of an exercise wheel or a change in diet. And so in humans, you can think about relational memory in a couple of different ways. For those of us who went out to dinner with friends or colleagues last night, the hippocampus and relational memory is what allows you to remember your experience last night. And so, you can think about and recreate that image in your mind of who sat across from you, who was sitting next to you, what the conversation was about, what people's interests were, what type of wine was ordered, and these sorts of things. And so it allows you to form relationships amongst the constituent elements of your environment. For those of us who don't know Copenhagen very well, I've been here a number of times, I still don't know it very well, using landmarks and navigating the streets of Copenhagen, which is not a simple grid like the town I live in, but yet a more complex town. Using those landmarks and remembering your way through the city to different shops or restaurants or sites is all done through relational memory as well. And so with that, in the laboratory, we recreate relational memory paradigms in a much more simplistic fashion. You can see along the top here, what we've done is we've paired for children different creatures and different environments. And we ask them to remember which creature goes with which environment. And so they spend their time studying, they spend their time studying these creatures and environments, and then later on we test them. And we ask them which creature went with which environment. So they had to form a relationship. We use another type of memory as a control. We call it item memory. This occurs outside the hippocampus. And here we use the same background. It's a skyline of Boston. And we use different creatures, and they simply have to remember, did they see these creatures before? Just simple identification. And so using tasks like this, we've been able to look at differences in aerobic fitness. And so these first data are cross-sectional. We had 49 children. They were 9 and 10 years old. And they were fairly equally distributed into either higher fit or lower fit based on measures of VO2 max, which is a measure of aerobic capacity. And we had kids perform the item and the relational memory task, and we imaged their hippocampus, as you can see up here. And what we find is that higher fit kids have greater hippocampal volume than lower fit kids. We find this effect bilaterally. And when we look at performance on these memory tests, you can see that while performing the relational memory task, higher fit kids outperform lower fit kids, since this is a hippocampal dependent task. When we look at item memory, we see that there's no relationship. And so we've had discussions about the selectivity of these effects on specific brain regions. Now, another example, and more recent work in my laboratory, has looked cross-sectionally at dietary lipids. And we've collected information about nutrient consumption and diet from different set of children, also 9 and 10 years old. And importantly, we parceled out things like fitness. So we look at, we use a large battery of information. We parcel that out. And so what you're looking at is the effect, the relationship of different diets on, or different fat consumptions on hippocampal function, relational memory function. And what you see is that along the top, you're looking at omega-3 fatty acid. I know that there's going to be a symposium on omega-3s, and this is some data that might sit well with that group. And along the top, this is our omega-3 fatty acid, and what you find is a selective relationship between increased intake of omega-3 and relational memory. And you can see that the effect is just a trend here for item memory. When we look at more of the Western diet, the typical US diet, we see down here saturated fat intake. We also have sugars and refined sugars and things of that nature. And you can see a negative relationship between saturated fat intake and both relational and item memory, suggesting that these different modes of training, if you will, have differential effects or differential relationships with memory performance. And so another area of cognition that we look at is cognitive control or executive function or executive control. They're fairly synonymous with each other. And this is our ability to orchestrate our thoughts and actions in accord with our internal goals and our mindset. And so importantly, this type of cognition occurs through a vast network that involves the prefrontal cortex. And generally speaking, cognitive control can be separated into 3 different types of cognitions. We have inhibition, which is our ability to ignore distraction and stay focused, or our ability to operate out of will rather than out of impulse. Working memory, our ability to hold information in our mind and manipulate it based on, and then use it later on when necessary. And cognitive flexibility, which we oftentimes call multitasking. So our ability to perform multiple tasks at once, inhibit one, execute the other, inhibit the second, execute the first. And so just to keep with a couple examples before I really dive in, here's some work on diet. This slide's a little bit confusing. I'm sorry for that. But if you look on the left, this is dietary fiber intake. Dietary fiber comes through whole grains, fresh fruits and vegetables, those types of nutrients, or those types of foods. And this is an inhibition task. Keep doing that. Clearly I need Mike's training for hand coordination. And so this is an inhibition task, and you can see with an increase in dietary fiber, we see an increase in performance on an inhibition task. When you look at the right, while the trends are going positive, those are actually cost measures. And so what you're looking at over here are saturated fats and dietary cholesterols, and you're looking at the cost to cognitive flexibility. And so what this means is that with more positive numbers are related to poorer performance. And so these nutrients are related to poorer performance on tasks of cognitive flexibility. And so secondly, going back to fitness, these are data in 55 10-year-old children. And what you're looking at here is are aspects of the basal ganglia, different regions of the basal ganglia. And we're looking at the differences in volume between higher fit in orange and lower fit in blue. And we're looking at different volumes. And what we can see is that higher fit children have greater volume in this subcortical structure, where in the caudate nucleus, the putamen, and the globus pallidus. And importantly, these regions of the basal ganglia are involved in the cognitive control network. It's thought that this is part of the network that orchestrates willed action or cognitions into willed action. And then, interestingly, these effects appear selective because when we look at the nucleus accumbens, which is not involved in that cognitive control network, but instead involved in aspects of mental processing such as reward and affect, we see that there's no relationship. And so with that, I'm going to spend a little bit of time talking about the Fit Kids randomized control trial. This randomized trial is has been basically the main focus of my work for 5 years. We're now into Fit Kids 2, so it's been really the focus of my work for the last 8 years. And this is an after-school program that we created in which children are bused to our facility each day that school meets. And so of the 170 school days a year in Illinois, kids came to our facility on up to 150 times. There were 221 children that were equally divided, and each day they received upwards of 70 minutes of intermittent, moderate to vigorous physical activity. And you can see there's a picture here of us measuring oxygen consumption, which is our gold standard measure of fitness. And importantly, there's efficacy in this after-school intervention, as you can see here, by children increase their VO2 max, or increase their fitness by just shy of 6%, where the weightless control group increased by less than 1%, which is probably the course of normal maturation. We used tasks that required inhibition and tasks that required multitasking or cognitive flexibility. And so these were tasks we had worked out through years of cross-sectional work that were child-friendly, and we found that kids can perform these tasks fairly well while still giving us a span or a range of performance. And when we look at change scores, what we find is that kids in the intervention outperformed kids in the wait list. And so when we look at that change from pre to post, we see that they improved their performance on these tasks from about just shy of 8% to about 10%. When we look at the waitlist control group, you can see it's about half of that. And so kids in the intervention benefited from their performance over the course of that 9-month period. When we looked at brain function, what we found, and this is a particular aspect of brain function called the P3, it's collected through EEG, and I'll talk more about the details of that on Friday morning. But basically what we're looking at is a change in activation following the intervention or following the weightless control. And as you can see, there's increased brain function following that intervention after parceling out baseline in the fitness group compared to the weightless control. And importantly, this aspect of brain function is thought to relate to the allocation of attention. Now, when we look at just the intervention group, and we looked to see how those kids performed against each other. We found an interesting relationship of approximately a dose-response relationship. I don't have a better term for it yet, but I'll say that cautiously, based on attendance. And so the more these children attended, the greater the change in that brain activation. And when we look at attendance rate, we see the greater the change in their performance on those cognitive tasks. And so other work in my laboratory recognizes that 9 months is a long period of time, and when people aren't physically active and don't want to be physically active, convincing them to be physically active for 9 months is not an easy task. And so other work in my laboratory has looked at single bouts of exercise. And how does one single bout of exercise change brain function and cognition for a short period of time? And so we took 20 children, they're 9 and 10 years old, and they came to the lab on a couple occasions. On one day, they sat quietly in a chair and for a 20-minute period. And on the second day, and these 2 days were counterbalanced, on the second day, they walked on a treadmill for 20 minutes at a very moderate pace, about 60% of their max capacity. This is an easy walk. No child was unable to perform it, and they didn't sweat or complain or anything of that nature. So, in fact, it looked to be fairly enjoyable. And when we looked at that same aspect of brain function, we can see that there's greater activation following the bout of walking compared to rest. And importantly, that activation was even greater, the change is even greater under conditions that require the greatest amount of inhibition. When we looked at their performance, we can see that in the condition that require the greatest amount of inhibition, we see a significant effect such that there's about an 8% increase in performance on this task. And when we looked at academic achievement, we found that there's an increase in academic performance for reading and math achievement following that bout of exercise. Now, through several studies, we've replicated this effect now 4 or 5 times in my laboratory. I'll show you one more example. But importantly, what we figured out is that the effect lasts about an hour and not much more. Interestingly, what we found out is that it doesn't appear to occur right away either, and we're still trying to figure out the timing of how closely after the cessation of the bout of exercise that it emerges. Now, in a second study that I think may be more relevant to many of the people in the room, we replicated this effect in children with ADHD as well, as you can see here. Following exercise compared to rest, we see an increase in brain activation. We also had another group of typical or healthy children, and we can see that both groups showed better performance on this cognitive task following exercise compared to rest, and they both showed increases in academic achievement as well in math and reading. Now, just a couple, I have just 2 more experiments I'm going to show you before I wrap up. With the focus of our work on physical inactivity and a lack of fitness, as well as increased consumption of poor dietary foods, naturally we've spent some time studying childhood obesity as well. And so these are data from that were collected from the baseline of that Fit Kids intervention. And when we looked at the children, it was actually rather interesting. Through the first 3 waves of the intervention, we took any child that could pass our screening and come in and had the time to allocate towards this intervention. And what we found was that 66% of the children in Urbana, Illinois that were part of our intervention were overweight or obese. That's an awfully large percentage. We found that 60% also fell in the bottom 3% for fitness. This is a school district that doesn't have physical education, and only some grades have recess. And in addition to body mass index, we also collected measures of DEXA, which is a gold standard measure for measuring different aspects of body: fat, muscle, bone, water, and those sorts of things. And we, in particular, were interested in a measure of central adiposity, or belly fat. And what we found was that with increased central adiposity, we saw increased cost of inhibition and working memory. So as you can see, with increased central adiposity, we saw decreased performance on these 2 aspects of cognition. When we looked at those achievement tests again, we found the same effect, or same relationship, I should say, that with an increase in central adiposity, we saw a decrease in test performance in reading, spelling, and arithmetic. Now, lastly, I'm going to sum up, before I sum up, I'm going to talk about one other experiment. We also have some cool technology. I was selfishly trying to fit into all four categories that Jens talked about. And so we have a virtual reality cave at the University of Illinois. And I actually have been asked several times, when you look at, given the measures that we collect in our laboratory, what do we really care about real world? And is it possible to look at this in real world experience? I don't know, but we can get close with a virtual reality cave. And so one of the things we looked at was the leading cause of death amongst children in the United States under the age of 16 is motor vehicle accidents. And this doesn't just include being in the car, but it includes being at the crosswalk. And so being on a walking or biking, it can be dangerous. And so given what we know about fitness and physical activity, we asked, might fitness relate to the ability to make decisions at the crosswalk? So we put children in the six-sided cave, and we gave them a treadmill, which is a manual treadmill, not an automatic treadmill. And so they have to move the treadmill based on stepping and pulling the belt back. And we just say at the onset, higher fit kids did not cross at a faster pace. We were able to measure how quickly they crossed streets, and the speed of gait did not differ between higher and lower fit kids. It was really about decision making. So we asked kids to cross the street under 3 different conditions. One was just simply to cross the street. The second one was to cross the street while listening to music that before they got into the experiment, we sat them down in front of our iTunes and filled an iPod with all their favorite music, and we put the earbuds in, had them cross the street. And then the third time they did it, we gave them a cell phone. And we had an experimenter who acted as a confederate in another room, and they held a conversation with the child while they crossed the street. Things like, what's your favorite subject at school? What team do you root for? These sorts of simple questions. And all they had to do, as I said, was to cross the street and walk through the tunnel. If they didn't, if they were hit by a car, you heard brakes screech, you heard a big bang, everything turned red. It wasn't very pretty. And what we found was actually, the work was very similar to what we found in our laboratory. Higher fit kids outperformed lower fit kids across the various categories. And so we saw a generalized effect of fitness. But what we noted was that higher fit kids statistically maintained their level of performance regardless of the level of challenge. Where lower fit kids, while showing a decrease in performance during the undistracted condition, they showed slightly greater decrease in performance while listening to music and a significantly greater decrease in performance while talking on the phone. And so it appears that in a pseudo real-world example, at least, we're able to find relationships between fitness and performance on tasks that require aspects of cognition. And so in conclusion, hopefully I've made a decent argument today for the relationship between fitness and its ability to benefit brain health and cognition. We have preliminary evidence for specific brain structures, but we have certainly stronger evidence for fitness effects on brain function. The fitness-cognition relationship is stronger for tasks that require aspects of cognitive control and hippocampal-dependent memory than even though we do find it to be a generalized effect, we certainly find it to be both general and selective. Excess adiposity appears to be related to decrements in cognition, as well as brain health and scholastic achievement. But I should caution you by saying that we don't know the direction of this relationship. We've not performed randomized controlled trials, and there's certainly a body of work out there that suggests that obesity, in part, is an issue of inhibitory control. And so certainly we need to follow that up. Dietary patterns appear to influence selective aspects of cognition as well. And so overall, what I would say today is that these data suggest that childhood health behaviors influence brain and cognition and may shape lifespan health and effective functioning as individuals progress through their idiosyncratic patterns of their life. Now, I'd just like to quickly at the end acknowledge my collaborators and my students who do most heavy lifting in these experiments, as well as my funding sources. Thank you.